Hi, I'm Doug Engstrom, VP Tech at Contemporary Research. Welcome to this AVIXA CTS course called Decisions in Integrating AV, RF, and IP Media Systems. For those interested in CTS credits, go to contemporaryresearch.com, search for CTS-RU. Follow the links to the Decisions course, register, and take the. When you're designing a media distribution system, you've got to make a decision based on one of three basic solutions: AV switching, IP switching, and an IP or RF multicasting IP system. This can be confusing as there's a lot of technology, jargon, and new acronyms to learn, plus a lot of marketing hype to decode. In this course, the goal will be to break down the choices into basic terms of origination, distribution, and integration. Thank you. Let's look at the various choices in terms of how they're structured. An AV switch system is something very familiar to us in the AV business. We're going to have a switcher at the beginning with X number of inputs and X number of outputs. That's going to be sending the signal to a receiver through UTP cable, these days using HD-Base-T, to carry both the video, control information, and a little bit of Ethernet to the receiver, making it a complete control system. An IP switch system, IPTV, changes the architecture, and we have encoders to begin with, and they'll be feeding in a switch somewhere in the middle of the system, and then that switch will then patch to decoders. And the nice part of this architecture, we're using an off-the-shelf 1 gig or 10 gig switch, and you're free to use any number of encoders or decoders as long as the switch system supports it. I define the two separate systems that use the same architecture as an IP switch is more of a switching, and you're expecting to go immediately from one image to the next with very little delay. IPTV is going to use H.264 encoding, which is more highly compressed, but it's not going to be a quick switch from one video to the next. Digital RF systems are also based on IP, using MPEG-2 or H.264 from encoders, and those will be collected into one combiner, and then all of those channels are sent in the same cable to all of the TVs in the system. And you'll have splitters and taps and amplifiers in the middle sending the signal through. And generally, the decoders are built into the TVs called tuners. But those are the systems you have, and those are the architectures you're going to follow in your design. Looking closer at AV switching, we already know it's a central switch, and controlling media are sent usually through HD-Base-T packets to receivers. The video is uncompressed, up to 4K 60, 8-bit, 4-color, 4.2.0. Remember, you only have an 8 gigabit stream, so a full 4K image couldn't fit. So one would expect when you do 4K in current AV switchers, there would be some type of scaling or compression to put a full K image through HD-Base-T. You're going to have 0 to very low latency, depending what's going on with the system. The streams are pretty heavy, going from 1 to 8 gigabits in a system. The wiring will be dedicated up to 300 feet, or you'll go fiber for longer runs. The chipsets are typically proprietary. I use that in a loose way because they're made by HD-Base-T, so that makes it proprietary. They're supposed to be more universal, interoperable, but I still don't think a person with Crestron is going to use an AMX receiver at the other end or somebody else's. They're pretty much going to stay within the same product line for the design. And those involved with more broadcast applications. SDI is also an AV switch system, but it uses coax to carry up to 3G 1080p systems, and there's also newer forms of SDI that can go beyond that. The newest switching scheme, IP switching, is one of the new popular things, and that's what everybody's touting at the shows now. And you will find that manufacturers of traditional AV switches like Crestron or AMX also have various solutions for IP switching as well. One of the differences, because you're using more moderate compression, you'll have to use at least a 1 gig switch, and some of the systems require you really get into 10G switches. The interesting thing, if you watch the marketing of these systems, all the companies now are talking about 1 gig switch. This is 4K and a 1 gig switch. And it goes all the way through the major companies, where 10 gig was the big news a couple of years ago. My expectation is that people have realized that when you go to higher bit rates and you get into 10 gigabit systems, number one, things get more dicey with copper cabling, and the connectors are not fun to put together, very complex. And so some of those systems in 10 gig have kind of had to gravitate to fiber rather than copper. And so I think there's been some pushback to that. And so companies are basically going to higher compression to get things going through the 1 gig switch, because that's where most of the market is 1 gig. Most of these systems are using some format of motion JPEG 2000 encoding. And that's basically, it's breaking up the video into individual frames. So when you have to switch at the other end, you're just going from one frame to the next. And it's free, and so it's very popular, and there are a few others that use some different ones, but the basic goal is your latency is about 0, roughly about 2 frames, and the compression varies with the need. So you'll see various terms. The main terms you'll see is mathematically lossless. That's when you're taking the video and compressing them by about 2 to 1. And that means if you measure it, there's not a lot of loss in video quality. Virtually or visually lossless means that there's no loss as far as you can tell, and that's about 10 to 1 ratio. There's another one they don't have a term for, but I'll call it pleasantly lossless, where you're really going to more 20 or 30 to 1. So when you look at companies talking about a 1 gig switch like the NMX and NVX systems, they're going to get to the numbers of like 100 to 900 megabit switching, you've got to do compression like that. By the way, for those video guys into new tech NDI, that is something like MPEG and JPEG called Speed HQ that basically is using kind of like MPEG technology, but you're just compressing one frame after the next, like you do with motion JPEG. And they go to that mainly because that format gives them transparency and alpha channel they can use for video production. But otherwise, your compression numbers are about the same as JPEG 2000. When it comes to encoding standards for IPTV and RF distribution, there are 2 sets of standards and then 2 sets of immersion standard for distribution. MPEG-2 has been out there the longest. It's still the standard for off-air channels, and it's also compatible for distribution and IP systems as well. MPEG-4 is the newer version of that. That's been around for several years. The advantage to MPEG-4 is that its streams are half the size of a comparable MPEG-2 stream. So if you have an 18 megabit per second stream in MPEG-2, that will only be 9 in MPEG-4. And typically we refer nowadays MPEG-4 as H.254, which is more advanced, better quality than the original MPEG-4 standard. Then you get to 4K standards, and these are emerging standards. The whole situation is not completely settled technology at this point. Number one, the primary battle will be for consumer, for people to pay extra for 4K channels that they watch on Netflix and YouTube and other programs. The other is commercial, where there's not as big a need. in commercial facilities, we really are not an entertainment system, we're an information system. News, weather, basic broadcasting doesn't need 4K for communication. In addition, most conference rooms aren't set up for 4K yet. You're going to need 100-inch screens, higher ceiling standards, and different viewing standards to make 8.265 or AV1 4K standards really work within a commercial environment. So the first that we've seen in the market, and you've seen a lot of this, is H.265 or HEVC. Its benefit is that it intends to take a 4K video and then broadcast that at a stream the same size as MPEG-4. That really hasn't happened yet, but the streams are smaller and getting smaller, and the latency is going to be very long for encoding because you have to scrape the video for more information to try to squeeze all of this into a smaller space. For homes, you have to be aware that your current Wi-Fi system may not be able to handle 4K channels. You might need to get your TV or box set on a wired internet connection before you can stream a 4K channel and not take down other things in the Wi-Fi system. So there's still a bandwidth situation for HEVC for consumer use and more so for commercial applications and networks. The latest standard out is called AV1, and that's a group composed of Comcast, Netflix, Apple, and many other large suppliers. Microsoft are involved, which basically want a more efficient codec and also one that is free of royalties. HEVC would like to charge consumer streamers for every stream that's going out, which can amount to billions of dollars, and the larger companies involved with streaming really aren't in with that program. So presently, AV1 has been released a few months ago. It's out there in the marketplace. It will probably take till 2020 before we see commercial-grade chipsets that have AV1 inside. So for the next couple of years, what is going to be the actual standard for 4K and other types of streaming is not yet established. For consumers, sometimes you're seeing HEVC, sometimes you're seeing Google's standard VP9 for 4K. And that's easier to do in consumer sets. When we get to commercial accounts, I think a lot of people in networking are going to wait until that battle is settled as far as what is the national default standard, de facto standard for images. So over time, we are going to see MPEG-4 and MPEG-2 around for a long time. And for commercial applications, there's going to be this whole battle between a couple competing standards for carrying signals, at least over the next 2 years. And then we'll have a clearer picture when that ends. I group MPEG systems like IPTV and RF in a separate category from switching because the encoding has much more compression and has much more latency. You never get to zero when we're talking about MPEG compression. MPEG is an interframe encoding system, as there's not individual pictures. Each frame is looked at and compared with other frames. So it begins with a group of pictures. The first one is an actual compressed image similar to JPEG, and all the other frames that are captured after it look at that frame and other frames and next to each other to compress the whole video as small as possible. So they have to reference all the frames together to figure out the best compression, what has moved, what colors have changed. And so each frame after the first one is not really a picture, it's more a data set that describes what changed since the first frame, and it's instructions to a decoder on how to put this puzzle back together again. As a result, you do get a good compression. Typical H.264 is going to be about 170 to 1, and so it's very efficient, especially for handling 1080i, 1080p. So a DI stream is 1.5 gig, and it'll be shrunk down to 9 megabit in an H.264 stream, a lot smaller. However, because you have these groups of pictures, a decoder, when you switch channels on a TV or your DirecTV box, has to snag the next group of pictures, find that first frame, that first picture, and then it has to capture a few more frames down the line to figure out how this is reassembled back into the something that looks like the original video. So that whole process from beginning to end is going to take about a half second if you have a very efficient system. It can take much longer depending on whoever is making the encoders and decoders for a system. Now that you've encoded the channels, you need to look at how you're going to distribute it to various TVs around a facility. And RF distribution has been a popular choice for a couple big reasons. Number one, it's based on a national standard, so that I could use encoder B and that'll play back on TV A, B, C, D, E, F, G. So the way the channels are assembled, the frequencies they're at, the encoding that I use, whether it's MPEG-2 or H.264 is standard, and the cable system called QAM that we use to modulate and insert that stream onto a channel is standard, and the TVs know how to decode the stream when it gets there. So these days, most newer TVs can also decode H.264 as well as MPEG-2. So there's a little more variety in channels that you can send. And each typical channel carries 2 HD streams. However, there are ways that you can also use that same channel to carry a 4K stream, because the encoders, modulators don't care what kind of stream, MPEG-2, MPEG-4, HEVC. It simply puts that stream onto the channel and shoots that out there. So once you have a 4K stream, most modern TVs that you get this year from Samsung and LG and others already have codecs inside for HEVC. So they're ready to go when a system wants to add a couple 4K streams to their systems. The TVs already have tuners built in, and like I mentioned, most of the newer smart TVs and commercial TVs are friendly with all versions of MPEG for your system now and the future. One benefit of RF, it's very passive. So you might have one amplifier in a system, maybe a couple in a very large system, and you could mix fiber as well in the system. There are systems like Z-band that can carry the RF over Cat5 wiring, and bandwidth isn't an issue because all those channels are being sent exactly the same time. All those streams are active at that moment. So when you get something from the cable company, you're getting hundreds and hundreds of video channels through the same coax that you would use in a commercial system. So bandwidth isn't a big deal. Either HD or 4K, it's not an issue in RF distribution. It just isn't bandwidth as a problem. And the RF is a very long distance carrier where you can go way beyond 300 feet. I mean, coax is being used for about a mile from fiber boxes in most cable companies today. And inside a building, fiber is pretty rare. We will find fiber used to extend coax in large arenas. They're using thousands of TVs. But it's not a problem. It's a good carrier of signals. And it's 24/7 because there's no real maintenance to do or support. There's no intelligent switchers in between. There's amplifiers that seem to run forever. And so it's a very system that's easy to install, easy to maintain. There's just not a lot of technology as far as a single coax going to splitters and taps throughout a system. So it's a very passive distribution system. And that's one of the key things to using RF. IPTV distribution requires a more active delivery system to carry the signal from the encoders to the decoders. First, you would need a 1 gigabit multicast switch, either as a central switch going to TVs, say in a sports bar, an immediate area, or it's distributed. There might be a couple different switches in the system, depending on how many TVs and how much distance is involved with sending the signals. The nice thing these days, it's not as difficult to set up a switch for multicasting as it was some time ago. Basically, I go to my Cisco, I turn on multicasting, turn on my multicast courier. We'll be talking about that. And that's it. There's only a few other settings, and so it's not as complex to set up as it has been in the past. You have to look at, can the network support the bandwidth? One of the quick rules of thumb is take 30, which stands for 30 megabits, and multiply by the number of encoders. That gives you a basic idea of what kind of bandwidth overhead you're going to need for the operation of the system. And then you're going to need independent IPTV decoders for each display that you have. And your setup, operation, support, and bandwidth is a lot easier if you have a standalone IP system. Obviously, if the stream is carried over a site's normal LAN or many LANs, it often requires that your in-house IT team to manage, and they're going to be involved in the system, because now you're just taking a simple system like one switch going to 24 or 48 TVs to now I have sites that have multiple LANs actually within the system. So there's a lot of work that has to go to manage sending the streams from one LAN to the next LAN to the next LAN to the next LAN, and it's quite a enterprise to get all that set up. And like I say, usually for a facility you need a very good IT team who are going to set that up, and they're going to have to manage that over time, because all they have to do is play around a little bit and they take you down or you take somebody else down. So there's a lot of planning that going over the site. So for that reason, when you talk to a customer about the different methods of distribution, very often you'll find the IT department saying, we really don't want that to go over my network. And you have to understand, for like Goldman Sachs, there's a lot of financial and secret stuff going over. They don't want to bother that network for video, and which isn't the most critical application over data. So you have many sites. I know Goldman Sachs in particular, we do a lot of their installations. They use RF to carry news and information around the system rather than IT. And they use IT for what it does best, immediate warnings, alerts, talking to people, sending emails, and normal communication within the system. So those are kinds of the things you're going to look like when you're talking to the customer. Don't be surprised if the IT team, who always said, hey, forget that coax, we got to use IP, we're happy to do it. And then you actually talk, well, let's really do it. And then, well, I don't know. So it's good to get them involved front end to know what their feeling is, and then you know which way you need to go with your system design. The way you set up an encoder for multicast is much the same. The difference is you would set the mode to multicast, you would put in an address, but this will be an address for a special reserved set of addresses just for multicasting. In this example, we're using 239.27.0 and the last one 27. You could take your computer or decoder and go anywhere within the system, and if you enter that address, the system will pick it up. And this kind of routing is called IGIMP, and let's cover how that actually works. The settings that you made set up a whole communication going on within the switch to make streaming happen between encoders and servers and players, decoders, and PCs that might want to watch the streams. The old way things were done, a unicast, was very simple. As shown here, you would have a unicast address, which is an actual address of some PC on the network. And that has to be set up in the encoder. So when that stream starts and you enter UDP-A/1235 in VLC, that particular computer at that address can see that stream and nobody else. Obviously, that's kind of a very limited way to make a network stream, and you'd find this very rare in today's networks. IGIMP Internet Group Multicast Protocol, which is the last time you'll really see all those words together. They refer to a process of messages sent across the network that manages streams and how they happen. Again, we've set up the switch for multicasting, we set it up for Querier, we set it up for leaving, and here's how the messages go. Now again, in a modern switch, you see the image of a router and a snooping switch. Nowadays, all of that's together in the same switch. So in this switch, you would have a host, which would be a PC or would be a decoder on the network. It requests a URL that 239.27.27. Now the querier is always sending messages through the network, asking, does anyone have a video that you want to see? Does anyone have the video that you want to see? And that snooping activity means that the switch that you're plugged into detects that you want to watch a video. So it says yes to the message, and then the router, in this case the switch itself, takes the stream and sends it to the host and plays it. Now, if several people on the same switch want to watch that same video, it'll just make a copy and pass that to the devices on its own switch. That saves the whole network the need to have multiple streams traveling to the network to that switch. I'm only sending streams out to the ones that want it, not every PC on the network. So when you get to a larger network, it saves quite a bit of overhead because we're not sending all the streams through the network, just the people who want it, and just to the switch that is managing the system. And at the same time, when you stop the decoder or go away from the stream on VLC, that will leave a leave message on the switch. And that same querier is also sending messages, does anyone want to leave? Does anyone want to leave? And the switch says, yes, this person has left, and it will stop the stream to that port. So that's how iGEMP makes all of this work together. It sounds complicated, but it's actually quite simple. It's just the switch saying yes, knowing that you want to watch a video, passes it through, and when you leave, it stops the stream. So a lot going on, but it makes it very simple to set up a network and just send the right address, and you'll see the stream. When we talked about RF and IP as distribution systems, we noted that a TV has one advantage in that the decoder is already built in. All you have to do is hang the TV, connect the coax to it, it'll scan for channels, and then you can use a remote control or control system for the user to select channels. That's not quite the same in IPTV. Even though you have smart TVs that can do Netflix and YouTube in the system, their apps are designed to go to server systems, subscription system that are outside the network. They usually don't have the ability to put a list of programs in there to listen to the same type of channels that are in-house being broadcast within their own network. They just don't have the ability to see a UDP address 1235. Maybe someday that will change, but that's the state of the art today. So you need some other tool to get the streams to the TV set, projector, or some other display. One of the places you start with in the process is something simple like VLC. It's a great geek tool. It's available, and works great for an integrator is that once you've set up your multicasting, you can go out on the network anywhere, insert your computer, and enter the UDP address, and then play it back on your computer and see how the stream is performing. However, that's not the same kind of user interface you want to give to an executive who wants to watch NBC News. So you're going to have some type of decoder box outside the TV. One type of system uses what I call a push link, and that is a control system inserts an address, much like the address we have on the screen, and that starts the whole iGEMP process going, and then the system plays that program through the decoder. If you want to stop it or select some other system, you're going to have to do some type of control system that's going to listen to your request and put that URL inside the box and play that particular stream. The other way to do this is to have a playlist already inside the unit, all the typical channels that the person would want to have that are available at that room, at that site. That's very similar to how TVs work, and allows you to have something as simple as an IA remote, much like a TV set. You do channel up, down, enter the channel number 2.1, and watch the video. Ideally, on a playlist, that list of channels and addresses can be inserted over the network. Some of the early sets, you had to have a keyboard plugged into the unit and manually type these into blanks and then save that. Not exactly friendly once you've got these hanging 10, 20 feet in the air. So one of the aspects you want to look for a playlist is make sure that can be updated on the network. Now, once you have a decoder capability positioned, then you have to look at, well, how is this going to be integrated in a particular room and across the facility? And the various ways that are out there, one is, like I mentioned, you can use infrared remote going through a channel list. The other way would be UDP or telnet commands coming from a control system or some type of web service within the network. And then the other question is, can I control the TV? So if can I turn the TV on with the same infrared remote? Can I change inputs on it and it can go back to select channels? And if you have control, one of the big challenges you're going to have is this device going to operate as a static device, where you have to get a list of static addresses set by the IT department, or can it work on DHCP, where you can just put these on the network, they automatically have an address, and then you have a discovery tool that will find all the units and allow you to define the operation, the addresses in the unit, and what the playlists are going to be, and you can address that and discover them once you've installed them on the network. So the other question, are you going to do a proprietary open standards system? So, for example, if you're going to do a Crestron system, that's going to be pretty much staying within the Crestron family for very often the encoder side and also for the decoder side. Other companies that do large-scale systems tie everything in with the software. So if they've got a high vision system at a site and they call you up and say, hey, I'd like a decoder to add to this one room. Is there something I can use? Well, it's not like hanging a TV because there are a lot of proprietary things going on with that system, and they're going to have to get that decoder through high vision, some other decoder on the system. You have to be aware of the fact that some systems that you go into are locked in place via the software and how things work. And some are more open standards where you can put a player, get the playlist in there, insert the addresses, and as long as MPEG-4, MPEG-2, it'll play the video back and everything is fine. So those are the considerations you have to look at. What are the capabilities of a decoder in your control system and multimedia system? Setting up multicast is a lot easier than it used to be before, as newer managed switches have IPTV multicasting features inside, things that used to be supported by another router. Setup is not all that difficult. This is a page from a Cisco switch, but most other level 3 switches have the same type of editing capabilities. We tend to kind of like Luxel because unlike most network switches, the indicators are in front and the connectors are in back, typical for an AV style rack. The basic steps you're going to do is you're going to set up iGIMP snooping, and you'll check that. You'll check immediate leave, which means that when a video is over and the person is done with it, you drop that stream right away. And then you set up an iGIMP courier, and that will pass messages through the system to make multicasting go. Those are the basic steps. There are many other settings you can have that set up DHCP and other networking tasks, but doing multicasting today is usually a matter of making a few settings and then the routers and switch is ready to go. One key thing to mention when we get into ideas of integration of IPTV systems, if you look out there and you make decisions, now especially for me, I've been a long time integrator, and then for the past number of years I've been with Contemporary Research, another integration friendly kind of company. I tend to look with a close eye on who I'm partnering with when they use the word integration. There are a lot of systems, especially in the IP switching category, that I would have to say are more IT companies rather than classic control companies. So I kind of have questions myself on how well integration happens over a room or integration systems. And so you have to have, for yourself, eyes wide open as far as how this system will be managed and networked, where will your support come from. So kind of a plug to our Crestron AMX. Any established control system and a relationship that you have, just any old encoder decoder system with a little Linux box that you buy with some kind of GUI, you click one thing and click the other thing, may not be what the rest of us would call an integrated system. So you have to be aware of what's out there and really look at what they're doing and really looking at the support. Now, it's contemporary research. We mention it because we're one of the few people doing a very unique style of facility-wide integration, so I need to cover this subject too. We have made for years a system called Display Express that typically has been used over RF, and it controls large areas of facilities. So Superdome has this, AT&T centers have this, the Spurs have this. A number of major stadiums and baseball parks are using this technology, mainly because we can broadcast a control channel all the way through the RF system, so they don't have to run CrestNet or Ethernet to all the TVs. They can get their channels and control for the same coax cable. And the basic idea is this: you have software like we make. You could also use a Crestron system. You have generic control commands that you send and that travel over the RF pipe, sneaks in between channels at 4 and 5. And a box at each TV picks that channel up. And the actual control codes are inside the box, whether it's infrared or 232. So the commands are very generic, like turn on, turn off, go to this channel, turn the volume to this level. And the box interprets that and controls the TV based on that instruction. So you can create your code, if you're rolling your own code, very generically, because they're just power commands with addresses, and you can change out the control code that's in the box so that if your Samsung TV turned into an LG, you don't have to change your programming code, you just change the code that's in the box. That's the way we've been doing it for years. Since that time, we've also branched out. We have the QIPD that's coming out. It's an IP decoder, but it also has those control codes inside, and we can also, from the same software, broadcast a control command to devices on the IP network. And so the same command that I send over RF can go over IP, and the box reads, oh, it's a code for me, and does whatever is needed for the TV or changes the channel and works the box. So it's a very simple system that works well over IP. And in the case of Display Express, you don't have to know how to write code. You just have control panels and devices you can set up to send the control code and presets that happen, all by filling in the blanks and making presets and control panels. But we have an equal number of systems that are doing that, plus they're doing Crestron, especially where there's sports bars in the facility that need somebody right by there to control it. Sometimes they use mine, sometimes they use the Crestron system. It's all fine. But the basic idea, you have an idea that has a mindset to doing integration, and we like playing well with other people or using our own software. We just like to see that you have a system designed to be integrated and designed to be supported as well. So we return to our 3 designs for signals within a facility or a corporate location. AV switching is good, especially for a narrow area of coverage, and it has an advantage because the signal is uncompressed and the output cable, Cat5 or Cat6, is carrying one signal. It's not sharing signals with any other program, so it gets easier to build large matrix systems and have the overhead to pass the signal through. IP switching is becoming more common. largely because the companies that make AV switching systems are now making IP switching systems. Again, it is switching because you have zero latency between frames. The signal will be more compressed, and there will be two solutions you can choose from. One, standardize on less compression and passing through cables designed for 10 gigabit systems end to end. That has its own issues as far as wiring, and many times instead of using copper, you find yourself using fiber for making the connections. I see the systems that are compressing the signal down to pass through a 1 gigabit connection to be a lot more practical solution for day-to-day switching systems. You can handle HD and you can handle 4K, though largely more compressed. But you can use simpler Cat6 cabling methods, 1 gigabit switch for making a little switching system, or a larger switching system if you go to a 10 gig switch with 1 gig connections between endpoints. For our company, we look at RF and IP as one universal system. The codecs are the same, so our encoders can distribute the channels as a QAM channel for RF distribution or as an IPTV channel for network distribution. And we do have sites that are using both pathways, RF to handle the major load and IP to take the signal to rooms and areas that do not have an RF connection. In addition, the video and control system is the same. So the control signals that pass through RF are the same control signals that pass through IP. So the programmer and developer of the system, or a web control program, doesn't care whether it's RF or IP. The control commands are the same for both, and you can have either solution or both in a facility and have it work in a seamless way. I hope you enjoyed this session, and I've tried to clarify things as much as I can. I hope you make good choices, and we're always available for questions at any time. Again, thank you for taking this course, and you can go to our website, search for decisions, and find our course, take the test, and get CTS credits. Thank you.